Now following dimension, we are given an option to select the frequency. This we can change. See, initially I told you that you should consider that okay, my antenna will resonate, my antenna will work in this span of frequency, in this bandwidth. So I can want a megahertz bandwidth, I can want a very low frequency, that means of the Hertzian scale, hertz bandwidth, or we can want a normal range for planar antennas, which is the gigahertz bandwidth. So you can choose between this, whether hertz or kilohertz or megahertz or whatever. Some very high frequency antennas may rise to terahertz or picohertz also. So we will keep this to gigahertz normally. These other options we need not change, these are system defined and the system will work properly if these options are selected. So once you select this, millimeter, gigahertz, nanosecond, Kelvin are already selected, click next. Then the second last option in this initial setup is defining the frequency. I mean, I want to simulate the structure. I want to see the results within a certain range of frequency that we can give the system. So suppose the minimum frequency which I want is 1 gigahertz is automatically coming because we have selected the frequency you need to be gigahertz only. And maximum frequency, we can keep it to anything. Let us say 12 gigahertz or 10 gigahertz, whatever you want you can do. Next is, you will instruct the system what will it monitor, what results you want, that you need to inform the system. Whether you want E field, electric field, H field, magnetic field, far field, power flow, power loss, whatever you want, you can instruct the system now. So in the project that we are planning to carry out now, we will select this E field, H field and far field. Now see, the moment you make these selections, some frequencies already gets defined. Among these two, what will get defined? The terminal frequencies will get defined here, 1 and 12, and a central frequency, 6.5 gigahertz, it is selected. Now this means that the system will actually tell you that I will be giving you the results at these frequencies. The system is telling us. But it may so happen that we want the results in some other frequencies also. So how to input that data? See, 1 semicolon 6.5 semicolon 12 is there. Suppose I want to add frequency 2 gigahertz. So after 1 semicolon, we will put 2, again a semicolon like this. Suppose next I want at 4.5 gigahertz, for example. So 4.5 gigahertz. Now one thing we have to remember, that these frequencies which we are defining here should be in order. That means I can't put 4.5 following 6.5. They have to be in order. So after that 6.5, now say we want at 8 gigahertz, 8 semicolon. Finally, I will add one more. Let us say 10 gigahertz. Okay. See, 1, 6.5, 12 were defined by the system. I am informing the system, okay, this is fine, but I want the results at some other frequencies also. What are they? 2, 4.5, 8, 10. So I have added them, putting in proper order. Okay, suppose this is the thing. Next, see one thing, that we have defined the template, we have defined antennas, we have defined what type of antennas, we have defined the solvers, we have defined the units. Now we are defining the frequency. So that is basically done. All the definitions are done. Now once you put next, the system will finally confirm that this is the thing which you have selected. Antenna, time domain solver, units and the frequency settings. Okay. Here you can change the name of the template if you want. Okay, antenna planar, because antenna planar 1 is already selected in my system. So it is auto selecting antenna planar 2. You can change this. Okay, you can change this name. Suppose antenna trial. Suppose I'm changing the name. Now one thing I want to alert all of you here. If you click finish here, then whatever settings you have already selected, that cannot be changed unless you change the template altogether. So if you want to make some changes now, suppose instead of 8 you want to add 9, you have to go back from here. You have to go back from here, make the changes and again come back to this. Because once you confirm that yes, that is okay, we can work with this, you cannot change. So this again I will name as trial here. You can change this actually. Now say let us suppose that this is the final selection that we have made. So after doing that, we will click finish. After you finish, then finally the working screen will come. This is how it looks like. Initially, this is how it looks like. Now see, this screen can basically be divided into 5 regions. This top region, this central region, this one at the left, this one here and this one here. This top region is mostly known as the command panel. This left region is known as the navigation tree. This central region is known as the working plane. This left one is basically the dialog box. And this right region is the comment box. Now what are the functions of these 5 regions? The top portion, this top panel basically gives you command what you can do or what you should do, operation wise, function wise, what you can do, that will give you these options. For example, you can model the structure, you can prepare the structure, you can simulate the structure, you can analyze the simulated results and you can view the simulated results. Fine. So from an operational perspective, this top panel will serve you the purpose. Next is, if you are designing a system progressively and you wish to look how the system is looking like at the end of every design step, the working plane will actually show you that thing. This one, the navigation tree. Suppose you are simulating and after a simulation, you will get different results. Okay, maybe the bandwidth you will get, the radiation pattern you will get, the gain you will get, the efficiency you will get, many parameters you will get. So how to access the results, how to verify the results, how to see those results? You can see every result and every design component from the navigation tree. If you want to give any special command, that you can do in this dialog box. If the system wants to tell you any information, maybe any error that has been occurred, maybe any alert messages, that the system will do in this comment box here, bottom right, this portion. So this is basically the flow of the screen, which portion of the screen will give you which particular information. Another thing is mandatory, and I should suggest you that always, there is an option to hide this coordinate axis, but never do that. Keep this coordinate axis in its position because it will immensely help you to actually design the structure and getting track of the structure, how you are designing or what you are doing actually. So let's proceed with the design. So firstly, we will be modeling the structure. So we will select this model. And if we are designing a microstrip patch antenna, as already mentioned, there are basically 5 structural parts that we will be designing. In an order, in an hierarchical order, these parts are, first we will design the substrate. The substrate is nothing but a dielectric slab. It is not metal. It is a dielectric slab on which the radiator, the metallic radiator rests. That is the substrate that we will be designing first. Second is, we will be designing a patch, which is a primary radiator. We will be designing the patch. Third is, we need to feed the patch with energy so that it can radiate. So the third third part which we should design is the feed line. The fourth part, since we are designing a microstrip patch antenna, we will, in most cases, in 90% of the cases, we will need a ground plane. Now the ground plane can either be on the same side of the substrate as the patch, or it can be on the opposite side of the substrate as that of the patch. It can be on the back side of the substrate also. I will tell you the names of the two structures as we design. So that is the fourth part. The fifth part is basically designing and creating the waveguide port, which is nothing but the connector. That means the external coax cable where it will be connected to the actual feed line. That port, that connection, that junction, that is known as the waveguide port. So that is our final structure to be generated in the hierarchy. So let's proceed like this. First we will design the substrate. The substrate generally is a rectangular parallelepiped structure. So I think all of you know that what a rectangular parallelepiped looks like. A cuboid sort of a thing where the sides are rectangles, not squares. So rectangular parallelepiped structure we will design. Now see here, under modeling, there are different options. This is the brick, this is sphere, this is cone, this is torus. Torus means basically an annular structure. This is cylinder. Now imagine how a brick looks like. A brick is actually a rectangular parallelepiped. So if we want to design a substrate which is rectangular and a 3D structure which we popularly call as rectangular parallelepiped, we have to select this brick. And for designing any rectangular structure basically in this CST, we have to select brick only. So let's see how it is done. We click on this brick and then we have to press escape button on your keyboard. Then this dialog box will come. Now once this comes, what we are designing the substrate. So we can name it substrate. Substrate we have named. Now here we need to give the dimensions. Here a very important thing I will be telling you. See, the dimension we can only comment upon, we can give the data on the dimensions if we know where our coordinate axis is. If our coordinate axis is at the end, at an edge of the structure, then basically that particular edge will start from x equals to 0, y is equals to 0. From the basic concept of coordinate geometry, we can say that. But here it is advisable that you fix up the coordinate axis, you imagine the coordinate axis to be at the exact center of the structure in the lower plane. So if the coordinate axis is at the exact center of the structure, then basically it gives us a benefit of selecting the coordinates for the x and y axis. See how it is done. Suppose we want to design a substrate whose overall dimension is 60 cross 60 millimeter. That means along the x axis it will be 60 millimeter, along the y axis it will be 60 millimeters. So if we select the coordinate axis to be at the exact center, then 60 millimeter length along the x axis, we can select the coordinates to be minus 30 to plus 30. Total it will be 60. Same for the y axis. The coordinate axis is at the center. So 60 millimeter along the y axis will start from minus 30 to plus 30. So we will do that. X min becomes minus 30. X max becomes 30. Y min becomes minus 30. Y max becomes 30. Now the question is Z min. We will consider that the origin of the coordinate system is at the bottom plane. So Z min is basically 0. Z max is basically defining the thickness of the substrate. how thick the substrate is. Now generally the substrate, the thickness of the substrate can be anything. But considering that it should be put under practical implementation, that means it should be integrated in any large system block, we keep the thickness value to be very small, around 1.5 1.6 millimeter. Generally industrially it is used like that way. So Z max we are considering to be 1.6. Okay, we don't have to do anything with the component, because component means the different layers that the structure will have. The system will take care of it. We don't have to change this component. Next is this substrate which we are designing, we have to define the material for that. Now as I mentioned that this substrate is basically a dielectric material, it is not metal. Now see whether we are having any options like that. We are having basically three options. First is this PEC, which is the perfect electric conductor. Obviously it is a metal. Then we have vacuum. So we won't use either of them. We need something else. We need a dielectric. Okay. So since it is not in the list, we have to load it from the material library. See this option, load from material library is there. You have to click this. Whenever you click this, the material library will open in front of you, and this will give you a huge choice, a vast range of materials that is basically available for developing the structure. And these are basically in alphabetical order. You can see air, alumina, aluminium, lossy, lossless, aldon. These are different types of commercial substrates. What we will be using in our project is FR4. See, if I go to this F, see FR4 lossy, FR4 loss free is there. We will consider lossy because we need to take care of the losses in the system as well. So what is this FR4? This FR4 is basically fire resistant epoxy resin version 4. This is the complete name of the substrate. Fire resistant epoxy resin version 4. Now why this particular substrate is used? This particular substrate is used as it is very easily commercially available at very cheap cost also. Secondly, this is mechanically very robust. What I mean by saying mechanically robust is we can give any shape to this substrate without rupturing its contour, without actually breaking it. You can create a square substrate, you can create a circular substrate, you can create a hexagonal, pentagonal, whatever you want. You can do that without actually disturbing the entire structure, without breaking. Now imagine if you are working with a very brittle type of material which is breakable. If you want to give it a complex shape, it may break. Such a thing is very rare in case of FR4 substrates. So we are using this FR4 lossy substrate as our substrate material in this project. Now see, if you select this FR4 lossy, its material properties will come here. What is the permittivity? What is the permeability? What is the loss tangent? What is the thermal conductivity? Everything will come. We need to verify whether the epsilon, whether the permittivity of this particular material is 4.3 or not. Why this value? Because commercially available FR4 substrates, they have the permittivity value of 4.3. There is an option to change this permittivity value also from material settings, material properties, but we won't use that now. We will just check whether it is coming to be 4.3. If it is yes, we will load it. We will load it. Now see, previously FR4 was not coming in the list. It was PEC and this vacuum only. Now it has come. So we have given the dimensions. We have selected the material. Now we will just preview to see whether how it is looking actually. If we can see the preview, we will press OK to finally design. See preview, it is showing. We can zoom out. It is showing, the contour is showing. So put OK. So the substrate is defined. See, the substrate is defined.